Okay, ready to go. So how are we doing? Any questions about homeworks, quizzes, anything? We have about just a couple of weeks left, so we have to finish. Okay, so let me quickly remind what we're doing today. So we're actually, well, this week we'll be talking about the file systems, and the idea is that by the end of the week we will assign a homework which asks you to extend x86 file system with new features. So it's important to understand how it works. Let me quickly remind, in general, what is it we're trying to build? So the file systems allow you to essentially share the physical space of the disk between multiple processes, right? So, and again, so the way it looks is something like this. So you have one single disk, right? So it has a disk space, meaning that it's somewhat similar to physical memory. So it has blocks, and instead of being addressable in terms of individual bytes, you can only address units of 512 bytes, meaning that the disk will not read you an individual byte. It will just read 512. And there were historical limitations for that, and now people are trying to resolve them with non-volatile persistent memory, which is byte addressable memory. But there are some additional limitations to that as well, so it's not really clear what the future will be, right? But the idea is that this is the disk, right? So it's just flat physical address space. Roughly imagine this room full of chairs, and you somehow say, look, if you want to use some of those chairs, and say that you will hold I don't know, a group discussion or something. Someone has to assign you individual blocks to make sure that, you guys are sitting together and stuff like that, right? But what we've seen before, there's kind of a huge gap between this raw disk space, which is almost unusable in any meaningful way, right? And an interface which we want to provide. So something like open, which takes the name of a file /foobar, returns a file descriptor, and then something like a read, which takes this file descriptor and a buffer and a len of this buffer and writes it to disk, right? So in the end, this write will end up somewhere here. So the data pointed by this buffer, right? It's the buffer is inside the process address space. Whatever is here gets written somewhere on disk, right? Conceptually, I mean, if I assign you a homework, the thing will be to design all the layers in between to make sure that, we somehow figure out where this data has to go, right? So essentially, how do we know where to write it on disk, right? Because there are multiple layers of abstractions in between the disk and this interface of a file descriptor. So let me just, because last time I was probably trying to do some kind of a bottom-up approach, but let me quickly do a top-down just to understand just for everyone to understand how it works. So this file descriptor, remember, it's a pointer, and a proc data structure has a file descriptor table, just simply an array of pointers. So essentially, this file descriptor points to an element in the array, right? So file descriptor is an integer, so we use it as an index. This pointer inside this array points to something what we call a file, right? File is the logical, essentially, it's something what we can name, something like foobar. Just to illustrate the idea why we need a file, imagine inside a different process, we also do open, and we just call, /buzz. And it so happens that in your operating system, in your file system, you decided to create something what is called a symbolic link, meaning that the same unnamed file, which we will call an inode in a second, is known as two different names. maybe this is not even needed in this example. Let me just do this. Just simplify it a little. Just let me, because this is probably just complicates the example. Let's just step back for a second and do the following. We say another process opens the same file, again, foo-bar, right? And it also tries to read, but maybe it tries to read a different location of this file, meaning that, despite the fact, maybe it's a large file, maybe it's some kind of a, I don't know, database, and we read these processes read different parts of it, right? The way it works is that this process will also have a process data structure, will also have a file descriptor table. And this file descriptor will be pointing to somewhere in this table. And this pointer will also point to something what is called a file. Why do you think let me ask a question. Do these guys point to the same file structure in the kernel? File data structure in the kernel? Probably not, but why? Not exactly, but that's a good question. So look, if I draw this boundary, let's imagine that this blue line is a boundary between privilege level 3 and privilege level 0. Remember that all memory of the kernel is mapped into all address spaces of each process, right? Let me also draw another line here. So this is process 1 and this is process 2. So the upper parts of the process memory are different, right? So it's like maybe one is running cat, another is running Apache web server. But the kernel is the same, right? So the moment you cross the boundary in the kernel with a system call interface, you can have a data structure which is like it's the same. If you will have a pointer, just for the sake of example, imagine there will be a pointer to something from here and from here. This something can be the same, right? In fact, it will be addressable through the same address, right? So the same pointer value. Is this clear? Because it's kind of important to understand that. Remember, I keep saying, I don't have a handy slide to show right now because in this lecture, but remember the yellow part of the address space is always mapped each process and it's always known. You cannot use it because it's protected, right? So you cannot just make up a pointer into the yellow part because it's mapped with without the user accessible bit, but it's there, right? Is this clear? This is more important even than the file system. So this is what we need to understand from this class, right? But then, okay, if I bring you back to this diagram with two files, we could have done the design choice, mean that we are reading the same file. It's foo-bar, right? So one can ask that this pointer should go to a single file data structure, right, in a kernel. But is it the case? And if not, why? I agree that it's not the case, but can you tell me the reason why? Or try to guess the reason. I don't think you know it, but. No, remember, the answer is somewhat simple. So, and unfortunately, there is no Ctrl-Z here, so I cannot really erase easily what I've drawn. But let me just erase all of these blue ones. The logic is the following. So each file has a position pointer. And when you open a file, that pointer can be reset to, let's say, 0, right? But then as you start reading, this position pointer keeps incrementing. So it is incremented by the read system call, right? And you can change the position explicitly by using a SIG system call. You say, look, I want to read a specific place within the file. So roughly speaking, the file itself, if I make a drawing here. So represents a logical view of the file, right? So it's kind of like, it doesn't exist physically, right? But it's one logical thing, which also has this 512 blocks, right? And each process has like tracks where they are reading. So in one process, the position can point to like block, I mean, some like, I don't know, it's like byte number 55. And in this one, it will be 1027, for example, right? Make sense? So that's why we have two different file data structures, meaning that two processes can read the same file, but as they read, each of them like has its own kind of position, which they're trying to access within the file. It kind of makes sense because they may be doing different things. One may be like adding records to the file and one constantly scanning the entire file to compute something over it, right? Make sense? Well, similarly, if we say, well, what if you open another file descriptor in the same process for the same file? Again, it will be like it will be a pointer to a new file structure, right? Because again, the same logic, it's kind of logically, those are like, you keep track of what's going on with those files and you can read them and do everything. However, if I ask you, like, this is fine, so we kind of understood how it works. The question is like, you want to see this file as logically continuous address space, meaning it starts from 0, then goes to 1 byte, 2 byte, 3 byte, and so on, right? But in practice, of course, because there are multiple files in a file system, those blocks of this file, they can be anywhere in a file system. One can be here, this one can be somewhere here, something like that, right? So we need yet another layer, which kind of tells us, which kind of tracks where those blocks, like logical block 0, logical block 1 within a file are on disk, right? And this is where the file systems introduce yet another data structure, which is called an inode. So specifically, an inode which is again a data structure. Roughly speaking, we can think of it, it has a tree-like data structure. It's not set in stone. It doesn't have to be a tree. It can be a linked list, and different implementations exist. But logically, it keeps track. It's kind of like a page table if you feel like it. So when it takes an input saying, okay, tell me where the block 0 of this inode is on disk, and the inode, this metadata which it tracks, and which, again, I will draw as a tree, will allow you to tell, kind of like a page table, to tell you, okay, by the way, it's in block number 57. Make sense? So it just resolves, like, okay, where's the block number 1? It resolves it and say, wow, and this one is actually inside the block number 88, right? So the difference between the file and an inode is that file only exists when a process opens it, right? And it also has a name. An inode exists when the system shuts down. So essentially, inodes, these data structures, these ones, are actually saved in some of these blocks on disk as well, and they are persistent. So if you shut down, you reboot, you come back, and you can start reading the same inodes again, right? Make sense? And in this specific, like the reason I was trying to do this example differently is that inodes, since they don't have a name, they can be referenced from different parts of the system. So you can create symbolic links and say, look, the same inode is known under the name foo bar, and as well under the name of whatever, home, a boards of whatever bar. That's just because I just said, okay, I wanna access this file from a different name, from a different place in my file system as well, right? So that's and those names are resolved into inodes by a layer of directory service. So essentially, directories keep track of, like, they are essentially, we'll take a look at them, but they are also persisted on disk. But roughly speaking, each directory is just an array which has a name, let's say bar, and an inode number. Inodes have numbers like, I don't know, 16, and says that the name bar, and bar is actually encoded as 3 characters, and 16 is an integer, and you say, look, in this directory, which, for example, represents home abortsev, or specifically abortsev, file name bar points to inode number 16. And I'll come back to it and explain how it works, but the high level overview is this, right? This is kind of like a top-down architecture of a file system. And we will talk now how to implement each of these layers to make sure that we not just have a high level overview, but if we need to modify or we need to build one, we can dive into the source code and essentially start working with it. Let me stop here. So any questions about what we're trying to build or trying to understand how it's built in xv6? Okay, so, and I don't know, like maybe people do understand how file systems work, so, or have a good hint. There is a couple of additional things. Okay, question.
Say that file makes sense.
Mm-hmm.
And it makes sense to use the files bits that you
Mm-hmm.
But I guess how come you said foobar is like you said foobar in quotes on the right hand side of the screen and home apron stuff. Those are both like references to an inode. Like when you read that, those are references to a file, which I guess underneath is really an inode.
Right. Okay, let me clarify this real quick. So let me edit. Let me quickly. I wanted to add a slide deck so I can quickly draw and make another drawing. Hopefully this is what's shared. This is what's get recorded. The way it works is the following. So there are special files on disk, which are called directories. They also are like each file on disk, like, okay, I say file. I don't know what the right word to say. Let's say, data objects, because I don't want to give them names. Like, let's put it this way. If you want to read something from disk, which may or may not have a name, you need an inode to resolve where it is on disk, like have this tree, right? So have this tiny little tree, right? So everything starts from a root directory, right? So when you essentially start reading something, you say, look, I know, like there is a convention. You say, look, I know how to read the root directory. I know that it's backed by a magic inode. Let's say inode number 0. Or it doesn't have to be set in stone, but you can read it from the metadata which you keep in a file system. You say that inode number 0 is my root inode, right? And this root inode, like, since it kind of represents a file on disk, or again, I don't want to give it, let's call it a data object, right? Because it's I don't know how to, like, what's the good name for it, right? But it says, okay, you can read and write it. Let's say you can read and write this thing through an interface of read and write an inode, read I, for example. And so essentially the kernel internally will read can read this, the content of this. It might be large, so it might spread across multiple blocks on disk, right? But internally what it contains, like all of it, this thing contains a table, which says something like I can have a file named cat, and it is represented by inode number 7. I have a file WC, which is represented by the inode number 16. And I have maybe another file called home, which is inside inode number 77, right? And so essentially what happens is that when you say open and you provide a slash home, I don't know, abortive, the implementation of this system call reads the root directory, figures out that it tries to like essentially descend into this level of, it tries to descend from the slash into the home. It reads the home. It says, okay, it's inode number 77. It then reads inode 77 from the file system. Inode 77 is represented, like also has like some number of blocks. So it has a tree. So essentially it will be pointing to this one. Internally, it may be a table as well. It not maybe, it will be a table. And there will be like, this is, if this is slash, this is home, there will be abortive. And it says it will be inode number, let's say 15, right? It's essentially, correct. It's just a mapping between the human readable names to inodes, right? And so obviously the mapping can overlap. So maybe inside home, we also have WC, and it will point to the inode 16 again. And this is called creating a symbolic link.
So I guess
Correct. And you can call it WC number 2, for example. Yeah. But they internally point to the same inode. So when you try to open WC, in the end, no matter how you enter this, through this pass or through this pass, they will all lead you to inode number 16. And then you read the content of the 16, right? And files, like, I mean, if you're probably doing a file systems, then you know these names and you know how they use. File is just, the reason is that the term is overloaded, right? So inside the kernel, file is just a data structure which will be pointing to an inode. And inode essentially, for example, will be pointing to the content of this inode, which holds the data for the slash for the root folder, right? Already confused? But anyway, so does it answer your question? So mostly. Okay, so let's, okay, any other questions? Let's go back here one more time. And do we understand at a high level that this hierarchy, but I wanted to come back and like add a little bit here. 2 other things. At a high level, we understand that this is what we want to build, right? There is a couple of things here. We want to add a caching layer here, which is called the buffer cache. And this buffer cache is a layer which allows us to avoid, like essentially it caches the frequently read blocks. So if we read this block 57, we put it in a buffer cache and we keep it there until it gets evicted, right? Similar to how we use caches on the CPU, right? Essentially, anyone who wants to read this block, like for example, this one, and instead of going to disk, we first will check the buffer cache and say, look, if it's already there in memory, let me just draw another line here. So this black one. So everything what is above the black line is in memory, right? So the buffer cache sits in memory, and it just periodically fetches blocks from disk to make sure, like, not when I say periodically, in x86, when it's read for the first time in a real operating system, there might be some prefetching policy that tries to like guess what the next block will be and read it ahead of time, right? So this buffer cache layer allows us to avoid going to disk all the time. So we just frequently access blocks, and you can imagine that blocks which contain the it depends on the workload, but for example, the root folder will be probably read quite often, right? Because we have to, like, every time we open a file, we probably will go through a root folder, right? And also there will be another interesting layer, which implements the consistency. So it's it's a layer of transactions. And it's hard to immediately see why it's needed, but often some operations like creating a folder or even writing a file trigger multiple writes underneath, right? And those writes, if only, like, imagine you write a file and it just, like, the write is big and crosses a boundary of multiple blocks. So you have to allocate all these blocks in a file system. So maybe some additional blocks like this one and some other ones get allocated for this write. And you have to update metadata on disk, which keeps, like, remember this bitmap area, like, I don't know, maybe it's sitting somewhere on disk over here, like bitmap. And you do some writes inside those bitmap, in the bitmap area, making sure that you say you mark those blocks as allocated already, right? And stuff like that. And imagine halfway through those writes, you lose power. And at this point, you come back and your file system is in some inconsistent state. And what you want to do, you want to say, look, I always want to come back to a file system which is some good state, right? Clean state. It doesn't mean that you will not lose information, because maybe you're trying to do like a write into a file and you lost power. You were half through that write. Obviously, a sane solution here is to say, look, you will lose all of those writes, because it's not like you lose half, right? But essentially, this transactional layer sits on top of the buffer cache and on top of the file interface, not on top, but beneath the file interface to ensure that you cannot break consistency, even in case of a catastrophic crash, right? So that's another layer, which is called journaling or logging. So we'll talk about this one as well, right? But this is how everything kind of fits together. And now my goal is essentially spend today and Thursday explaining each of these layers. I will start from like a brief overview of again, like I'll come back to the layout of the file system, and we'll start bottom up. So essentially from the buffer cache, then going into the journaling, then going into the file level, and to the naming level, which resolves names into inodes, like essentially directories into directory, like traversal and everything, and up to the file description level. Good, makes sense? At least the overview, right? Okay, so last time I was saying, okay, we need to represent the file system on disk somehow, right? And the way it's done is that, and again, it's just one representation, but this is how file system, x86 file system does it, right? So boot block is reserved for essentially for the boot protocol. So here we have like our 512 bytes of the bootloader, which BIOS fetches and the address 7C00. But after that, everything is a file system, right? And the way it works is the following. So you say, look, every time I start reading a file system, I need to start somewhere, right? So I need to understand how big it is, how many inodes, where is the data area. And so each file system will have this metadata block, which is called a super block, right? Essentially, super block contains information about all of these other areas, and roughly speaking, their sizes. And the moment you know the sizes, you know where they are, because you say, look, logging area is right above the super block. After that, inode area, and this can be variable size. So you need to know how many inodes you have. After that, you have the size of the bitmap area. And after that, everything is just data area, right? Okay, the way it works is that, remember, I said that inodes are essentially, they represent file on disks, right? So like the inode area is just an array. So essentially it's an array of inodes. And since it's an array, each of them has a number. So this is inode number 0. So this is like, it is really on disk. So every time you switch off power, next time you come back, you read this array, you say my root folder will be in inode number 0. So you will have to read this inode number 0, right? Internally, this element of this array is, again, it can be different, but in x86, it represents a tree. So essentially it says, okay, it will have a 12 pointers to the next level. So it's kind of like, it's a compromise, meaning that for small files, the file will fit into this first 12 entries, because each of these pointers can be, it's a pointer to the data block in the data area. So for example, when you read inode block number 0, you land on this element array element number 0 in the inode data structure, and that will point you exactly here, right? So this is where the beginning of your file will be. You say, look, I want to read block number 1. You go into element number 1, it points to some other element in the data area, right? However, it allows you to represent only small files. So roughly speaking, if you say you have 12 entries, it will be like 512 multiplied by 12, right? It's not a big file. In order to represent, make a compromise between storing small files efficiently and allowing bigger files, the last element of this array is a pointer to yet another level of the tree. So instead of like pointing to the data storage itself, it points to the next level of the file tree, right? So it's kind of similar to a page table, except that the first, in this case, I guess 11 elements or 12, I think 11 elements in x86 will be stored directly within the inode. So you don't have to read anything besides this inode from disk. But if you go for a bigger file, you say, I have to read this one, it's somewhere here. And then from there, I will traverse the tree, and then I will land on a real data area. You get this idea? It's just a convention. So you can design file system differently, right? You can say, look, I don't think it's a good idea, for example, because all my files will be big files. So let's not even bother with this first 11 elements. Let's just make sure that we can just make sure that inode keeps a pointer to the root of the tree, and then it just traverses the tree. Right here, they make a convention saying, okay, well, we want to strike a balance between small and big files, and the first 11 elements will be direct pointers, and the last one will be a pointer to a tree, right? Yeah, it will be not allocated. Yeah, and x86 uses a tree, but you can imagine, well, what if I don't like a tree? Because tree may be, the depth of the tree says, okay, that limits my, first of all, you can say the tree never grows and it has a constant depth. So in x86, I think it's just one level, and I will come back to it. But you can either have a bigger tree and have bigger files, or file systems like FAT, and you probably don't remember those on Windows. But instead of having a tree, they had a linked list. So essentially, they allow unlimited files of unlimited size by encoding this, like by using a linked list instead of a tree, right? And if you want a larger file, you just add a new element to this tree, right? Makes sense? But this is how, again, we'll come back to inodes later, but just to understand how it works. So those inodes are like when you in x86, when you create a file system, you say, look, I want to support max number of inodes, and it will allocate space for them right above the journaling area. Make sense? After that, we have the bitmap area, which keeps track of essentially what blocks are available in the data area or what not. It's just literally a bitmap. If it's 1, it's allocated. If it's 0, if it's unallocated. And the way the allocation algorithm works is that it just scans through the bitmap and finds an unallocated block. Obviously, it's very inefficient as the file system keeps growing. The scan is longer and longer, and it doesn't fit obviously in a single data block on disk. So it's quite large, and then, it's not fun essentially in x86. So in a real file system, you have to make sure that this bitmap is stored as some kind of a tree as well, to make sure that you keep track of allocated and unallocated blocks efficiently. But x86 simplifies it and just says it's just an array. Make sense? In the data area. So inodes themselves, since they are stored in place, right? They simply have a flag, unallocated or not. So if you want a new inode, and this is what x86 is doing, it just scans this array of inodes and figures out the one which is unallocated. When you create a new file, it will just scan through this inode array and figures out a next unallocated one. Also linear scan, also inefficient. There is no tree in the inodes. It's just literally an array. Like you say, look, I allocate some number of inodes when I create a file system in x86. And I say, I want to support, let's say, 105 inodes. It will literally allocate 105 elements, rounded up to the next block, because you say, look, sure, whatever. And it will be inode number 0, inode number 1, inode number 2, and so on, right? Initially, file system is empty. But typically, when you create a file system, you will have a tool which creates a root directory, places some files, and updates those, saying, okay, this inode, it will update these 12 entries, and it will say this points to the data area. And in a data area, this is where my root folder will be located, right? This array of WC, cat, stuff like that. Make sense? So there is no hierarchy of inodes, right? If you try to create a new file, you have to scan from the beginning file, find the next unallocated inode, and just use it, right? If you ran out of inodes, that's it. You cannot create files. And a bitmap area keeps track of those data blocks here. They can be used for anything, right? They can be used for storing anything but inodes in x86. So for example, it can store directories, it can store real content of L files, WC. Of course, WC will be also represented by an inode, but then, multiple blocks in this data area will actually store the content of WC, right? And this bitmap keeps track of which of those data blocks are unallocated or not. Make sense? You mean, are you talking about wearing out the SSD? So SSDs are funky. So they internally implement another. In general, yes, you can say that, but SSDs have internal algorithms to kind of level out the wear, right? So meaning that they, literally when you're accessing block number 0 of SSD, doesn't mean that it will go to block number 0. There is a translation layer, which is called flash translation layer, which in fact, you cannot even write individual bytes. You have to write multiple, or blocks. You have to write multiple blocks in SSDs, right? So let's not go into this. So, but you're right that certain design choices of a file system might not be ideal for SSDs. And there are specific file systems which take into account this fact that you have to like average the writes over the entire area of SSD, and like those designs exist. I don't want to go into them, but you're right. But it's like a separate area in a storage community which does it. Right? Let's just forget about it for a sec. But yeah, there is that. Any other questions? Okay, cool. So now let's go into those layers. Like we got everything. We got the bitmap. We got the data area. We did this poll last time. So let's talk about the buffer cache. So the buffer cache essentially, like literally what we want to do is we want to cache frequently accessed blocks. It's not about inodes. It's not about anything. It's just any block in a file system. If we have to access it, we want to cache it, meaning that sometimes you can read any blocks like from 0 to like 0. You typically don't read in a kernel because you don't care about the bootloader, but only when you occasionally update it, right? But maybe you want to read some inodes frequently. So you want to cache this block because it contains this inode, or you want to read the bitmap area frequently because you want to like add and delete files, or maybe you want to like essentially access actual like content of a specific file. Maybe it's a directory like a root, or maybe it's WC or whatnot shell, right? So each of these blocks can be cached by the buffer cache, right? So buffer cache is generic, so it caches everything, right? The way it's done is the following. So there are two goals. Like I keep talking about caching. This is for performance. The second goal is synchronization. Synchronization means that at some point you may ask a question like, what happens when two processes try to write into the same file? How the access is synchronized. And essentially, buffer cache synchronizes the access at the level of blocks. Essentially, they say if you try to write the same block, like essentially maybe two processes open the same file, they're trying to do a write into that file, I keep saying file because we call a file in a file system, but they will open inode. Maybe the file is known under different names, but they try to write the same inode, same block of the inode. So you will have to like synchronize at the level of a buffer cache, making sure that only one, like they will take turns, making sure that there is some consistency, right? How one can build a buffer cache? Just literally think of a buffer cache. What's the easiest way to build one? Your goal is to, every time you read something from disk, like a block, like bring a copy of the block to memory and keep it around for a while, and then maybe flash it back to disk. What will be your choice of the data structures to build this? So, well, roughly speaking, x86 again simplifies everything quite a bit. So what they do is the following: is they look, we will have this data structure be cache, like that's the definition, to literally have an array of buffers of n buff size, right? And each buffer is this data structure. It will represent a buffer which will read from a disk, right? So essentially this B size field is 512. It matches what we read, right? So essentially when we read something from disk, we will read into this array, right? And this global array just represents the entire content of the buffer cache, meaning that you say, look, the buffer cache can cache n buff blocks from disk. Essentially, when you read, each of this will contain the 512 bytes which will read from disk. Make sense? It's not hard. So say, look, that's one way to build it. So it's in memory. In fact, since it's global data structure in x86, so it's in a data section of the kernel, right? So here, buffer cache, each block in a buffer cache will be in a specific state, which is defined by this flags field. It can be either busy, currently is locked, and one process is trying to access it. It can be valid, meaning that the data was read from disk and it wasn't like it's in an up-to-date state. It can be dirty, meaning that someone wrote into this block and it has to be flushed to disk before essentially evicted, before being evicted, right? Sure. So buffer cache has a pointer to a physical disk because operating system can boot with multiple disks, and so this device pointer is a pointer to a disk. Every time we cache a block, every time we read a block from a disk, we remember which block we read, meaning that it can be 77, later on it may be 16 or something like that, right? And we maintain the buffer cache as a least recently used list, meaning every time we read something in a buffer cache, we'll try to keep it for as long as we can. And then essentially each of these blocks, they're kind of like maintained as a list. And as the block ages, stays in the buffer cache for the longest amount of time, it will be at the very end of this list, and it's a candidate for eviction because we're trying to use temporal locality here, meaning that you say, look, like if you access the block once, most likely you will access it again. So which means that like frequently accessed blocks will be promoted to the head of the list, meaning that if you access the block, you immediately promote it in x86, which means that the block will stay there. But if you haven't accessed the block for a while, it's a good candidate for eviction, right? Because we only have the nbuf blocks in a buffer cache. In x86, everything is like statically allocated. So in a real operating system, you can say, look, maybe we'll allocate more memory for the buffer cache. But in this one, it was just fixed size, right? Make sense? So it's a reasonable approach to build it. So the interface of the buffer cache are those like three methods. So they essentially implement the block read, block write, and a block release functionality. And this is how you access the buffer cache. The typical sequence, if you want to access a block from disk, you say, look, I will first read a block. This method will bring the data from disk into the buffer cache. And obviously, in order to bring something in the buffer cache, you need to essentially allocate space in the buffer cache. So it will scan for available blocks. Maybe we'll do some evictions. Then maybe you write a block. This write actually doesn't touch a disk. So it just gets written and retained in a buffer cache. And be release essentially says, okay, this block, the sequence is complete. So this block can be later either accessed by another process, or if it's evicted, can be used for caching another block from disk, right? Make sense? This is a specific implementation of how it can be done. So essentially, this is first an example. So for example, another part of the kernel which implements bits of journaling, this specifically does this sequence. It reads a block, writes a block, and releases a block, right? So essentially that's every time you try to access anything on disk, you go through this, right? So this read, write, and release. Implementation of a read, I said, okay, a read essentially tries to get the block in a buffer cache. So this bget method essentially says, okay, it tries to check for the hit first. Essentially, it says, okay, if the block is already cached in a buffer cache, then it's fine. I will just return a pointer to that block. And there can be different cases. Essentially, if block is not valid, it will actually be read from disk into memory. If it's already valid, it just immediately returns it to the reader, right? Make sense? And the beget internally, the goal of beget is to check whether the block is already in a cache. So x86 uses this kind of like a very brute force way of checking for the blocks. Essentially, it does a linear scan. This linear scan is a little bit amortized because frequently it starts from the head of the list. So frequently used blocks promoted to the head of the list, because it's to maintain the LRU policy, you always move them up into the front, right? And so essentially, the complexity is slightly, it's not that I can compute this complexity, like I cannot reason about it, but it's slightly better than just ON, right? Because there is some amortization of those reads, right? And so essentially it starts from the beginning of the list and it just goes from the beginning to the end. In the worst case, it's ON and it traverses the entire list. But essentially what it says, okay, I'm looking for a block which is read from a specific device and a block with a specific block number, because I'm trying to read block number 55. So I will scan this list, and if I suddenly have a hit, meaning that I found this block in a buffer cache, so I have a match. I set a flag busy, making sure that the buffer cache implements synchronization. So it says that other processes will not be able to access this block right away because I'm taking it on a first access and return it to the caller of bget. If, however, the block is busy, this is one example where the sleep function can trigger a yield and essentially say, look, I'm trying to read a block. Maybe I'm trying to read or write a file system, but really this block is currently used by another process. So here, the sleep method internally will code yield and internally will code switch, which we discussed last time. So that can trigger a context switch. Essentially, the operating system says, since we anyway have to wait for this block, let's better yield the CPU to some other code, right? Make sense? So first, linear scan to make sure that we try to find a block. If it's there, we're lucky, we return it here to the caller. If we're not lucky, xSys says, okay, sure, now let's try to find a clean block. And essentially it does another scan, and essentially it goes through the buffer cache again, trying to find a block which is not busy and which is not dirty, meaning that this block can be like essentially evicted, meaning that it can be reused for reading a different block number from disk. So, and this is what it does here. So it says, okay, I found a non-busy, non-dirty block, because dirty means that it has to be flushed to disk, so it cannot be used. And it says, okay, now it will be used for caching the block number, which the caller passed from a specific device. We set the flag busy, and we'll return this block to the caller. Make sense? So it's kind of the logic of a cache, essentially. It's a little primitive, so 2 linear scans. x86 is not cannot gracefully handle the condition when there are no blocks in the buffer cache. So it's just optimistically assumes that there will be one always. If not, it just panics at this point. You just cross the system, right? Make sense? And so if we return the block here from the bget, which we just discussed a second ago, if it's already in a valid state, just return it to the caller. If it's not, here this ID read-write function essentially goes to the device driver, this device driver, and reads the block from disk and memory, right? Another interesting method is brelease, and like as I said, it maintains the least recently used policy. So every time the block is released, it's promoted to the head of the list to make sure that, okay, it's not evicted, temporal locality, but essentially nothing super interesting happened here. Let's try to answer this question and wake up. So what I'm asking here is, okay, you look at the buffer cache, it's nice. What are the main flows? Like why it's not ideal and what needs to be changed to make sure that it can work a little better. There are multiple flows. Okay, I have a couple of answers. Uh, Okay, a couple of good answers are, okay, let me present. So linear time lookup, brute force loop is slow. So I agree with this. So this, despite the fact that this search is somewhat amortized by the fact that we're promoting the frequently used blocks to the beginning of the list, this search is slow. So how one would change this? What's the solution? x86 makes it simple. So it really just says, okay, yeah, we'll scan the list. Linux will do a better job, way better job. You can sort it, and essentially the way to do this is to maintain it as a tree. And if the tree is sorted, then you can quickly log and look up to make sure that essentially you, instead of searching through the entire buffer cache, you just quickly find unallocated blocks. Yeah, that's a decent solution. So what are the other disadvantages? So people said, okay, guys, it panics when it reaches the end. I agree. What will be a solution for this panic?
If you have something that writes one of the dirty blocks and uses it.
That's a good strategy as well. You say, look, because it's x86 says, okay, I will not try to flush the blocks. And the assumption here, I guess, that I think x86 assumed that every time the block, we should actually see, I think B release, no, I forget how the flush is done. But yeah, one possibility is to like, I think the block actually, every time you write, I don't remember. I have to figure out the flash. But yeah, you're right. So trying to solve this panic and try to find some blocks which are dirty and flush them, it's a good strategy. But maybe it will interfere with the logic of the x86 buffer cache. So you have to make sure that you patch it more carefully to make sure that if there is set an assumption that blocks which are busy, they cannot be flushed, stuff like that. So you have to deal with this. Another possible solution is probably say, look, let's go to sleep here instead of panicking. And maybe wake up later. Let's sleep for like a unit of time. And hopefully when we come back, we will find an available block. It's not an ideal solution because maybe it's like a denial of service. Maybe you will be sleeping for too long and you don't even know for how long you will be sleeping, right? So that's another clever observation that, okay, it's not ideal. What else people are writing? Buffer cache size limitation. Yeah, that's a good one too. So x86 says, okay, everything is allocated statically. So instead of growing the buffer cache, we have only n buffs there and we'll never go above this limit. So another solution for this panic would be, say, let's allocate additional memory to hold the buffer cache itself, right? Global lock contention. That's another very good observation. I didn't talk about locking yet. We will talk about them next week. But essentially, here, in order to synchronize access to the buffer cache, x86 acquires a lock, and it's a global system-wide lock. It's like a static variable bcache lock. Essentially, at this point, all other accesses to the buffer cache are frozen because any other process which tries to read something from a buffer cache will have to wait on this lock. And it's kind of a big showstopper. So essentially having such large lock, and as we will discuss next week, slows everything down by a lot. What can be a solution here? There's a couple possible solutions. How to avoid a big system-wide lock. No, you're right. So you should, ideally, you should implement locking at a finer granularity. So either your data structures like this linked list can be done in a log-free manner, which is a little hardish, but at least you maybe acquire the log for the list and then immediately release when you found something in the list. Another approach which Linux is doing is that they implement buffer cache not as a system-wide entity, but it's per file, meaning each file will have a tiny buffer cache. And which means that if you're at least reading different files, you don't contend for the same logs because logically you don't have to, right? So you just simply say like that's like we're not trying to access the same stuff on disk. They never overlap, so it doesn't make sense. So that's another way to solve this global log contention. Okay, cool. So maybe this is good enough. So like we understand the limitations of this, the buffer cache. Let me deactivate the poll. Let me go back. So the next layer which we want to build is this journaling layer. So how to motivate it? So the idea is the following. So imagine you have a complex file system wide or not, yeah, file system wide operation, something like imagine a file system, like, I don't know, maybe you're doing a write or a file descriptor. And this write essentially says, okay, look, I need to allocate a new data block on disk, which means that you have to go into the bitmap area and mark this block as taken, which means that there is another write into this block. And maybe since you're doing a write, you have to patch the mapping inside the inode to point to this data block. And that means that it's another write into the inode area, right? Just a single write, even into an empty file, like, I don't know, of a tiny buffer of 1 byte, triggers multiple writes to the disk. Does it make sense? So in this example, you have 3 writes. So the byte will go in the data area, another write, so it's write number 1, write number 2 goes into the bitmap area, and write number 3 goes into the inode to make sure that we remember where the data block is on disk. Make sense? Makes sense that it triggers 3 additional writes underneath, right? Now, what happens if you lose power right after the first write, this write number 1? Well, potentially you essentially said, okay, I wrote something, but I never reflected the fact that I allocated the block or added it to the inode. So you just simply lose a write. That's okay. That's not too bad. What happens if like you lose the power after write number 2? Here you say, look, you wrote the data, you mark the block as allocated in the bitmap area, but you didn't record the fact that this block belongs to an inode. What happens in this case?
You just currently lost some amount of memory.
Yeah, you lost this block because you marked it as allocated. And remember, I don't know if like you guys ever used it, but when I was younger, this actually happens. So a power loss typically results in a reboot of a machine. It always results in a reboot, but then there is this a tool which is called what was it called? Which scans the entire file size system, tries to figure out like blocks which are lost. What's the word? What's the name? FSCK, the tool is called, right? So it was quite common. So you can FS file system CK check, essentially a tool which scans the file system saying, okay, like I know that this block is marked as allocated. I will scan all the inodes and I will try to figure out whether this block belongs to any of the inodes. So you can kind of you can recover from this post factum, but it's sometimes hard and it takes time, right? But you see the point. So you have a leak, but you can have problems which are worse. So like if the operation is even more complex, you might have that maybe you, instead of issuing this write as write number 3, maybe this one was write number 1 actually, and this way you point to a data area, but you never wrote the data, or maybe you didn't mark this as even as allocated, and then this block gets allocated for another file, right? So how to solve this problem? How to make sure that we always leave the file system in a consistent state? Write them in parallel? Well, but what is in parallel? Like, there is no real parallel, because in case of a disk, if it's a spinning disk, in the end, the mechanics of the disk is that there is some kind of a head which just moves around and just writes one block at a time. If you lose power there, you kind of screwed. I mean, people were clever about it. They came up with the idea that, you know, this disk might have some additional batteries and will finish those writes, but that's kind of gets funky. So it's, you never know when you run out of power.
Well, where to leave it in a consistent state, store it in a buffer before the operation, and after the operation is completed, mark in the buffer that the operation is complete.
This is, I believe that what you're trying to get to is this idea of journaling, and that's correct. So let me explain it in details, but let me first discuss a couple of other opportunities. So anyone sees any other ways to solve this problem? Because journaling is a de facto standard way to do it. It's just prohibitively, it's not prohibitively, it's somewhat expensive because you read everything twice, and I will explain why in a second. But people were trying to essentially avoid this journaling. And one way to do it is always, it's kind of, you can always come with correct ordering of those writes in such a way that the last write commits the transaction in such a manner that only if this write finishes, you see the changes on disk, or you don't see them at all. This way, if you do a bunch of writes, like you do a write in the bitmap area, you do a write in the data area, this write into a bitmap area might be some funky write, but only if you do this last write number 3, then everything is committed, right? It's possible. This approach is taken in a FreeBSD file system. It's called soft updates. It's essentially careful ordering and reasoning about which write is really committing transaction. If you don't see this write, if you lose power before it, then everything is okay. It turns out to be very hard to reason about the orders of those writes. As operations grow in complexity, you have to be very, very careful. It's not impossible, but it's hard. And so people were getting it wrong. So essentially, like literally, there's just like a handful of people in the world which can maintain this file system because no one else understands what the ordering should be, right? In theory, you can like come up with a mathematical, like a more careful mathematical model, or have a mathematical proof about the correctness, but it's hard. And so instead, people came up with this slightly simpler technique. The idea is the following. It's called journaling. So imagine you have 3 candidate writes. One goes into the inode area, one goes into the bitmap, one goes into the data area. So in the end, on disk, inode will have to go here, bitmap will have to go in the bitmap area, and data will have to go in the data area, right? Instead of writing them directly to those areas, the operating system writes them in a special area in a file system, which is called a logging area or a journal. So essentially, this block is written here first. This block is written here. This data block is written here. So let's call them 1, 2, and 3. 1, 2, and 3, right? If you lose power at this point, those blocks they were not changed yet. You will see the file system as this operation was never even attempted. Agree with this? Because you only wrote them in the logging area. And after reboot, you come back and say, look, well, you keep track of what's in this logging area, and maybe you haven't written anything yet here in the header. And you just say, well, forget about it. Like, it's empty, we rebooted, everything is clean. The moment you finish these 3 writes, you write a number, roughly speaking, number 3 in the journaling area, right? And you keep track of where those blocks have to go. So 1 has to go here, 2 has to go here, 3 has to go here, right? The moment you roll this number 3 into the logging area, you committed the writes. If you lose power right after that, the system reboots. On boot, you inspect what is there in the logging area. You say this number is 3. It means that there are 3 pending writes, right? And sure, you can copy this write number 1 here, write number 2 here, write number 3 here, and move on. And then this means that this operation actually completes after reboot, right? Make sense? What happens in case you don't lose power? It's very easy. So you say, sure, I wrote this 3 into the logging area. I go forward with committing this transaction, essentially copying this block number 1 here, block number 2 here, block number 3 here, and then erasing the fact that I had a transaction, updating this logging area with 0. After that, you're done. Your transaction is complete, meaning that if you reboot and you find this 0 again, you don't have to do anything. Make sense? So what happened here is essentially you write everything twice. You never touch the final destinations first. You write everything in the logging area, and you remember that you did it, even if there is no crash or anything like that. And then you install those writes into proper locations. And if you lose power halfway, so essentially maybe you rolled 2, you did like 2 from here to here. Let me just change the color. And you didn't finish writing the 3rd one, you lost power, you reboot, you will still see the 3, and you attempt those writes again, and you finish 3rd one after reboot, and then you update it back to 0, right? That's called journaling. Well, then this write never happened. You lost the data. So for example, you try to record the fact that maybe you're launching a spaceship and you launched it, but you try to write it in a file system, you lose power. Well, you will be inconsistent with the external world, right? So the ship is gone, the power, there's no record of it. Yeah. It will not, because this number will still be 0. You only update this number to 3 after you recorded the fact that these 3 writes are destined to be written. You record 3 at this point, you say, look, I'm ready, I commit.
So this ensures consistency, but it doesn't necessarily mean that everything.
Correct. So, and it's an interesting problem, and it's still an active problem, like how to be consistent with the external world. And there are different techniques for how to deal with that, and there is no easy solution, but yeah, you can lose data. So essentially, but it's still better than just coming back into some inconsistent state. You don't even know whether you will be able to use the file system, because maybe some pointers point to wrong places, right? But think of it as a transaction. It either happens or not. If it doesn't happen, then you lost the fact that you're trying to record it, right? Okay, any other questions? Okay, it's a simple idea. Engineeringly, it's very, very simple, right? So implementing the journaling, like no matter the complexity, no matter, like maybe you trigger 1 write, like maybe you write 1 byte, as in my example, internally it triggers like a bunch of other writes to metadata in the file system. But this journaling essentially simplifies like everything. You don't have to keep track of the order of the writes. As long as you record them in this journaling area, you can always commit the transaction, even in case you lose power, right? The downside is that everything gets written twice. So roughly speaking, you lose half of your write performance. That's where people kind of like get split on this idea, saying that, okay, guys, really, it's nice, but we really lost half of the capacity. Can we do better? And that's why people go back to this idea of soft updates or something, like figure out a discipline which allows you to avoid duplicating the writes, right? But we got the point. Okay, so probably I will stop here and I will come back and explain organization of this journaling mechanism or implementation on Thursday.